I'm Stephen Belcher. I'm a graduate student at the University of Nebraska Omaha. I'm actually filling in for my colleague Anoop Mishra, who couldn't be here today. But I'm here to talk to you about AI techniques for evaluating visual search performance in glaucoma patients. So, it'll cooperate. We'll start with glaucoma. For those of you unfamiliar, it is an age-related neurodegenerative disease of the optic nerve, and it's the second leading cause of blindness. It causes a degradation or thinning of the optic nerve. It can be very painful, and it affects roughly 3.5% of the adults over the age of 40. So while that's a low percentage, that ends up being a lot of people, obviously. Central to this study is visual search, which in recent literature has been used as a tool to study human perception and cognitive functions like attention and memory. It is instrumental in our ability to localize target objects among competing objects within an environment. So here you see a couple of examples like finding the right item or brand of item in a supermarket, or searching in a crowded area for a familiar face. There are myriad other examples of visual search tasks, but the point is that it's very important to our day-to-day lives. So we have a hypothesis here, which is that the environmental scene context and image characteristics fundamentally influence visual search performance, specifically in glaucoma patients. Our objective then is to identify some relationship between these properties of the scenes and the visual search performance to improve our understanding of the way glaucoma patients perceive the world. To do this, we're proposing a conceptual model for evaluating visual search performance that involves the use of deep learning and image processing techniques. So we'll talk about the experiment design just briefly here. We use photographic stimuli from the Berlin Object In-Scene Database, or BOIS. It's a database of 103 images, and there are 3 variants of each. There's one that you see on the left here where a target object is in an expected location. On the far right, you'll see another variant in which the target object is present in an unexpected location. And then in the middle there, you have a version where there is no target object at all. And so this is sort of the flavor of the entire data set. And we'll be using 3 patient groups: patients with glaucoma, patients with ocular hypertension, which is a related disease, and healthy controls. And each of these patients, for each of the images in our data set, will perform the tasks that you see in this sort of flowchart down here. They'll be asked to fixate on a point. They'll be briefly shown the target object that they're looking for. They'll be shown that fixation point again, and then the image that they're searching for will come up. And so from the moment that image pops up to the moment that they successfully identify the object in the scene is the response time that we're using as a measure of their performance. Here you see a diagram of that process I've explained to you, and on the right you see a subset of the image characteristics like brightness, contrast, spatial frequency that we're extracting. And it's important to note that these characteristics weren't chosen arbitrarily. They have been identified in vision science literature as being meaningful to a variety of vision tasks, including vision search, and so that's why they were chosen. Moving on to the scene context, right now we are using a MassGar CNN model to essentially count objects in the scene and identify objects in the scene that draw attention more than others. We're working on fine-tuning it right now. As you can see, it's identified a variety of potted plants, especially around the object in question, or the target object. And this is allowing us to make sort of estimations and quantify the amount of clutter around an object to determine how busy or complex the scene is. And ultimately, we'll use that as a metric in our final analysis. We had hoped to have some preliminary data for you guys, but unfortunately, patient trials have been put on hold due to the entire pandemic situation. So to wrap it up, we are looking to address the current gap in our understanding of glaucoma and how it impacts patients. We proposed this conceptual model that I've just described to you, and we're using some deep neural network techniques as well as some image processing algorithms to extract a set of information that'll help us describe the image computationally. And based on the observed reaction time in patients, we're going to, of course, perform a variety of analyses to try and identify meaningful relationships between those image characteristics and altered visual search performance among patient groups. This ultimately could improve the quality of life greatly for glaucoma patients. Similar techniques have the possibility to be used for other patient populations that experience vision loss or cognitive dysfunctions. Similar strategies can be used by experts to develop other methods of helping patients in their day-to-day vision tasks, which of course provides a greater level of independence, which reduces burden on healthcare professionals and caretakers. And yeah, so these are our other collaborators, and that's all I have for you.